maybe the vacuum structure, maybe the space is the counterpart. Maybe in the space, which seems to be the force that's expanding our universe, and since this moment, you know, we found that not only is our universe expanding, but it's accelerating. So in order for that to happen, they had to put energy in the vacuum called dark energy, or the cosmological constant. And they had to add this energy to the vacuum to make it expand. So now we know there's definitely energy in the vacuum, and we can measure it. So that's at the cosmological level. Now let's look at the subatomic and atomic level. Oh my God, I gotta go faster. At the atomic level, I realized, reading physics, that, oh my God, they had found energy in the vacuum, and not just a little bit. Let's read it together. Present-day quantum field theory gets rid by renormalization process of an energy density in the vacuum that would formerly be infinite if not removed by renormalization. That is, when we looked at the atom in, you know, almost 100 years ago, and we start to calculate all the oscillations that would occur in space-time, in the structure of space inside the atom, in the 99.99999% and around the atom, we found that if we got close enough to the structure of space-time, it would be fluctuating with infinite amount of modes. That is, there's infinite amount of wavelengths that you can find smaller and smaller and smaller and smaller and smaller and smaller wavelengths to infinity. That's what the equations were saying. There's infinite amount of energy in the vacuum. And, you know, when I found this, I'm like, they actually found it. They found the structure of the connectivity of all things. They found the structure of the vacuum. But that was not their realization at the time. They said, oh my God. It was called a vacuum catastrophe. We got to get rid of this infinity. It's infinitely big. Ours said, wow, we found the source of creation, infinite amount of energy. Wow, how do we get in there? No. Instead, we renormalized it, which is okay, you know, when you're writing equations. But it's not so much the renormalization that's the problem, is that it was renormalized and then it was placed in the closets of physics for almost 100 years, until people many different inventors throughout the ages, and people like other researchers and I started to talk about this and make this forefront. But how did they renormalize? What they did is they used a constant called the Planck's distance. The Planck's distance is a calculation that's very valid as far as I can find. And certainly in my latest paper that I'm going to show at the end of this presentation, it's remarkable. And the thoughts right now is that the Planck's distance is the smallest thing the universe can do. It's the smallest oscillation of the structure of the electromagnetic field that can occur. You can think of it as a photon going through itself, or the time it takes for a photon to go across its radius, or its diameter. So you can imagine it's teeny. It's really, really small. It's 10 to the minus 33. That's like, you know, that's like a period with 33 zeros, right? That's a lot of zeros before you get a 1. It's really, really small. Now, do I think it's the smallest thing the universe does? Absolutely not. But I think that the Planck's distance is a very important scale for our relationship to our current size universe. That is, it defines a boundary level at the smallest, and the universe boundary defines the boundary level at the biggest, and that gives us, you know, a relationship in our scale. You guys follow? So I think it's an important thing. So what they did, I know the little Shanti dog wants to come up here and give some physics, but always get excited on this part, doesn't it? So what they did is they took little Planck's distances and they said, how many of those can we stack in a centimeter cube of space? And since each one of them is a little energy, right? It's a little oscillation. E equals mc squared can tell you how much the mass of that oscillation is going to be. And the mass is 10 to the minus 5, so it's very small mass. However, if you count all the masses of all the Planck's lengths in this centimeter cube of space, you'll get a density. How many mass per centimeter cube is there in the vacuum oscillations? And the answer is 10 to the 93 grams per centimeter cube. 10 to the 93 grams per centimeter cube. That is a big number. Okay? That is a really, really big number. You might have noticed in your bank account, you know, when you have like zeros, you keep putting new zeros, it improves rapidly. You know, if you have 3 zeros, you add another one, it's like, oh, nice, you know. You add another one, oh, yeah, no, that was good. No. You add another one, oh, yeah, now we're talking, right? So imagine you got like 93 of those, right? Things are looking good, right? Now let me give you an idea of what that number really means. If you took a centimeter cube of space and in it you squashed all the atoms in the universe, all the stars, in all the galaxies, there's billions of galaxies, each one has billions of stars in it, and squished them all into a centimeter cube of space, you would have a density in that cube. Imagine how dense that thing would be, right? You'd have a density of 10 to the 55th grams per centimeter cube. 10 to the 55th grams per centimeter cube. That is very large already, but it's 39 orders of magnitude less than the density of the vacuum, which is 10 to the 93 grams per centimeter cube. All right? You're swimming in an infinite soup of energy. You're most likely living off it. When you eat, you actually are replacing vacuum energy that you've desecrated. You are feeding off the vacuum literally, and you could actually bypass the eating part. And that has been shown. I've done it myself. And, you know, nowadays there's sadhus in India that are coming out of the woodworks to be examined by the medical establishments, and they're being isolated in a room for like months at a time. They don't drink, they don't eat, they don't defecate, they don't sweat. They live directly off the vacuum. And, you know, that's a being. Imagine that you got a technology to pull out of the vacuum. If we got 1/billionth of a billionth of a billionth of a billionth of a percent of what's there out, we would have enough energy to run the whole planet for thousands of years. Never mind the capacity to curve space-time, create space drive, overcome gravity, get off the surface, which we really, really, really need to do really, really soon, and so on. So, if this is true, we should be able to measure it in laboratory. In 1947, because you might say, well, yeah, that's all nice, but it's just equations. Maybe you guys are lost. Well, in 1947, a guy called Casimir, a physicist called Casimir, said, well, we should be able to measure it. If that's true, we should be able to get plates close enough together so we can eliminate the long wavelengths and just remain the short wavelengths between the plates. The result would be there would be more energy outside, less energy inside, and the plates should get pushed together, create a little gradient in the vacuum. When he did the calculation, he realized, wow, the plates have to be really, really close together, microns apart. Nobody could mill plates with micron precision in 1947. It took until the 90s before this happened. And in the 90s, when it did, then the plates got pushed exactly as was predicted by Casimir. The experiment was reproduced in laboratories all around the world, and now we even have results of a dynamic Casimir effect, or Unruh effect, and that actually pretty well proves unequivocally that the vacuum is there and that it has physical meaning, because almost for 100 years they said that this vacuum energy is way too big and it probably has no physical meaning. I think it's the foundation of all physical meaning, and that's a big difference. So, it really is there. Now, if this is true as well, then when we look at the universe, if they're basically just division of the vacuum, then all the pieces in the universe should be in harmonic relationship to each other. There should be some coherence in the way the vacuum divides, if the vacuum connects all things. And so, with the help of Dr. Rauscher, we wrote a scaling law to see if that was true. We started it, and the scaling law is radius against frequency, or you could think of it as radius against energy. And we started with the universe. Now, I would like to let you know that if you take the mass of our universe as we observe it today, and you stick it in a bubble in our universe that we see our universe size to be today, the universe obeys the Schwarzschild condition. It obeys the condition of a black hole. We live inside a black hole. That is, if I